Well, it's time. Welcome back. It's a small group today, but I'm glad you made it today, David. If it's just going to be us, then we'll make it work somehow. I think everyone's just kind of tired after getting through the third exam. Usually, the attendance on the Thursday after an exam Tuesday is not very great. So we'll get through it, like I mentioned. As far as the exam three grading goes, I'm going to begin grading on Friday. My hope is to complete on Friday, but it could extend into the weekend. The moment it is graded, I'll just upload the grades here as long as along with your feedback on exam three, the grading marks, solutions, and so on, just like we did for exams one and two. Aside from the other announcements, section 7.4 is due today. 7.3 was due yesterday. And if anyone's a little bit behind on those sections, it's understandable if you are focusing on these for the exam three. Sometimes it's a good idea to strategize and target the exam material. But I accept full credit even if you're turning in any material late. Well, that's pretty much the roundup of announcements. We're starting a new chapter. There's going to be 3 sections in this one, kind of a short chapter. And this is what we're going to conclude on for the rest of the semester. Any questions or comments at all before we get started? Okay, let's begin. So we are now in section 8.2. And again, I was just mentioning it's kind of a small class, but we've got an in-person representative and a Zoom representative. So we'll make it happen today. So here's our new chapter we're going to take a look into for the last content of the semester. Chapter 8 is on a topic that doesn't seem big at first until we start delving into it. Chapter 8 is on a so-called relations. 8.2 is their formal induction of what is a relation in the first place. And notice how small this definition is. That's it. That's the definition of a relation. We mean specifically a binary relation. There's a ternary relationship and so on. But for a binary relationship, we just mean a subset of A cross B. And that's the entire definition. There's a lot to say. Even though the definition is short, that doesn't mean there's a lack of structure inside here. And so one thing we should review when we are going to state a definition like this is go all the way back to section 2.4 and say exactly what we mean by A cross B. A cross B, if A and B are sets, both of them we assume to be non-empty sets, then A cross B is just a collection of ordered pairs, bracket A comma B, close bracket, such that A came from the first set, B came from the second set. And we took some time in this section writing out various cross products. For example, if A is xy, B is 1, 2, 3, then it's the set of all combinations of elements from the set A paired with elements in the set B. So the size of that set came out as 6. So again, it's kind of an amazing definition. That's the whole story until we delve into it a little bit further. Further notation is just referring to if the sets A and B happen to be the same, which is a common set of examples we'll see, then sometimes we, instead of saying a relation on A cross A or A squared, we just simply say a relation on A. And whenever elements are related, meaning xy is in the set R, which is again a cross product, we could sometimes write it in this notation. We'll use this often, set notation, as our author does. And occasionally, this is another common notation. To say an element is related to another, we write xry. To say x is related to y. And we've seen lots of interesting relationships so far. We've just never called them relations. In place of this r right here, one relation could be x equivalent to 3, or rather congruent mod 3 to y. If the relation is congruence mod 3, then instead of putting in the r, we would put in the actual relation, and that would be the thing we throw in. Or it could be a divides relation. If it's divides, we would write something along these lines. X bar y means x divides y for another relation. And there's a humongous plethora of examples. Many things we've been talking about were in fact relations. For another one, in place of R, you could put in the subset relation and write in A subset or subset equals, your choice, both of them are relations, of B. hang on, the highlighting is for the relation there. And if you've taken linear algebra, that A, B are matrices. Then we write a relation for row equivalents of matrices, A row equivalent to B in this way, if you've taken linear algebra. So as subsets, that would be a relation. And this is just a quick smattering of different relations that come up in our book. This one, again, excuse me, in the context of linear algebra. So again, this is kind of a gentle introduction to relations in 8.2. 8.3, we'll look into more properties of relations. And then in 8.4, we'll look into the equivalence class, great applications of relations themselves. Any questions at all, folks, with the first definition here? Okay, and here's another interesting side thought as far as relations come up. This definition we've actually used before. It was just kind of hidden. Our author is now going to actually cite this definition in the current section. And here's how it goes. If you're defining a function, we have our formal definition here, 2.46, that we used quite a bit. But I mentioned there's a whole nother way to define functions. You could say a function from a set A to a set B is a subset of its graph, which is a subset of A cross B. So all a function really is a subset, just like a relation. The function has one extra property. If A and B1, A, B2 are in F, or excuse me, G, the graph of F, then we assume that B1 equals B2. There's a unique output to every input. So if you take off that property, when we don't require a unique output to every input, you're talking about a relation now. We just took off a bunch of structure. It's no longer a function. And that's why this information starts to get even messier than functions are. You can define functions and relations in lots of ways. For example, one kind of a fast introduction thinking about the definition. This table is a great way to define a relation. We'll say that Earth is related to Luna because Luna is a moon of Earth. I decided to write it as Luna instead of moon because that would conflict with this heading here. So a table like this can define a relation, but it does not define a function because Mars has two moons and we have a specific direction, the planet being associated with the moon in that direction. So here's our really short example one to think about our first definition. We're going to let P denote the set of planets. That's going to be much like A here. M is going to denote the set of moons in the table above. That's going to be much like B. And a fast question, just for the sake of reviewing topics on cross products and cardinality, is what is exactly P cross M equal to? The size of it, rather. P cross M in cardinality, we've mentioned before, we don't have to actually compute the whole cross product of P cross M. We can partition this and say, with the multiplication formula for cardinality of sets, the cross product of P and M is just the size of the set M, or excuse me, P, multiplied by the size of the set M. So that's a nice cardinality formula to use. And again, we cited that formula or used it way back in this section here. The set A had 2 elements, the set B had 3 elements. So the cardinality of the cross product was just 2 times 3 for a value of 6. But it is tricky when you look at this, right? If you're looking at the table, you might say, well, the size of this set is 5, but it's not true. P is a set of planets. There are only 4 planets in this list. Mars is just duplicated because it happens to have 2 moons. So the cardinality of the set P is just 4 altogether. Multiply it by the cardinality of the set M. All the elements here are unique, and sets, when we look into cardinality, is only concerned about the unique elements when we say the size of the set. So here we can say 5, whereas here, just 4 elements truly. So the cardinality of P cross M is 20. Well, again, just kind of a review of what we've done before. It's kind of interesting looping back all the way to chapter 2, now that we're clear in chapter 8. We still haven't really even defined the relation. That's going to be part B. But what we looked at is the total set. A cross B could have a infinite cardinality. For P cross M, in our particular example, the cardinality is 20. And when we go to define a relation on our cross product, it's just going to be a subset of that set. So our relation can have at most 20 objects, but it's probably going to be smaller. Usually it's a proper subset. Here's our definition of the relation R. On P cross M, we'll say that XY is an element of R. So we're using set membership for our definition here. Because remember, if you say the relation is a subset of A cross B, you're specifically saying the relation is a set. So we can say the element is in the set R to refer to X, Y being related. So X and Y are related if Y is a moon of the planet X. So from that, we have just two quick questions. We're just determining set membership. Part B is asking, is Mars, and I think that's pronounced Deimos, related or in the set R? Well, looking at the table, Deimos is a moon of the planet Mars. And so we'll say, yes, this is true. Let's say it here briefly. Mars, Deimos, is an element of the set R, since, citing the table above, Deimos is a moon of Mars. So it satisfies that membership relation. Then, for a follow-up question is Titan Saturn related, or is it in the set R? Again, that's going to be always considered interchangeable. Often I'll say, is Titan and Saturn related? But the order matters here, right? If we say yes to this, we're saying that, let's follow the color coding. Y, Saturn in this case, is a moon of the planet Titan. But Saturn is not a moon and Titan is not a planet, which means this set membership or definition here is false. So we'll say briefly, Titan, Saturn is not related, not an element of the set R, since Titan, or let me say it more directly, since Saturn, or more in order, since Saturn is not a moon of Titan. Or hang on, let me get this order right. Saturn is not a moon. Yeah, that was right, of Titan. Got my ordering here just a little mixed up in my head. Well, it's kind of tricky in a certain sense because the information is here, right? Saturn, Titan. But what this second part in part B is really all about is the order of the elements does matter in relations. Sometimes you can switch the input and the output, the first element and the second element, but that's no guarantee. If it's defined in this way, Y is a moon of the planet X, then Titan and Saturn are not related. Well, that's relations so far. Any questions or comments at the moment? Okay, again, it's just kind of a fast example to kind of get a feel for what this definition in one sentence is really trying to say. The last thing we're going to do is, if a relation is a subset of A cross B, we can just write down that subset. And so this will be a common exercise that we're going to be doing in these notes and occasionally in the later sections. Write down the relation R explicitly using set notation. So now all we're going to do is say this relationship R, Y is a moon of the planet X, making XY related. It's in fact a set. It's a subset of the set containing 20 elements. But all we're really doing is just grabbing the table and reformatting it in this notation, XY element of R. So we just write down, going row by row, the ordered pair, Earth, Luna. And then it's kind of busy work from here. Just keep on writing these down. Mars, Luke, and Phobos. Mars, Deimos. Jupiter, Europa. Saturn, Titan. Now, once we have written down the entire relation is a set, exhaustively listing all the elements, definitely we see Titan Saturn is not in that set. It's Saturn Titan that belongs to that set. Mars Deimos definitely belongs. And again, it's really just reformatted the table is all we really did here. So it's kind of a fast exercise for the purpose again of just tracking that definition through. What we did, folks, that's example one down. We're going to look at a lot of different kinds of relations, kind of like what this is indicating. Lots of things that we do mathematically, we can just reformat, rethink about in this as a relation. And it's not just a mathematical kind of curiosity. There's some really great purposes for doing this kind of thing. And that's what section 8.4 equivalence classes is all about. So that's what this entire chapter is really trying to get into. Any questions before we change to a new example, new kind of relation? Okay, well, this course is on discrete structures, and this is definitely a discrete structure. We have a set with just 5 elements, but relations, again, can be a pretty big topic, and that's what example 2 is all about. We're not doing a whole lot in example 2, but just thinking about what a relationship could look like if we define it in this way. This one has infinitely many points inside this set, infinitely many things that are related to each other. We'll say R is the collection of all ordered pairs XY in R cross R. So we're saying the relation is now defined on R, but really we mean R2, R cross R is what we're saying there in the notation. And this is the only thing it has to satisfy. X squared plus Y squared equals 1. But thinking it back in terms of trigonometry, that's just the unit circle. So to express this relation geometrically, pretty much one way you could do this if you're keen on graphing, you could just explain what it is using ordinary words, but I think this is a fine approach as well. Just draw the unit circle. This is coordinates 1, 0, 0, 1, just to emphasize we have a circle, not the world's best drawn circle, but we'll go with that. And now we can say X is related to Y. That is XRY is one way to notate that. Or you could say bracket XY is an element of R is the next way to notate that. Our author happens to use this notation quite a lot, but mentions this is a fine way to notate it as well. So X is related to Y if, well, we just go to the set membership definition, X squared plus Y squared is 1, meaning I'll use our same bracket notation. XY is on the unit circle. So that's our relation there. It's kind of an interesting relation. Notice some things about this one. As these two coordinates kind of indicate, and they're not a coincidence if AB is an R, then BA is an R as well. And that's a pretty much guarantee. The order here, you can actually swap it because the check is x squared plus y squared is 1. You could just swap that to y squared plus x squared is 1. Algebraically, they're equivalent. Our last relation didn't have that property at all. If you switch the order of the moons and the planets, you're changing the meaning of what you're looking at. Because it does have this property, we can now say that this is a symmetric relationship. In the next section, the major properties we're going to be taking a look at are reflexivity. Symmetry is one of them that we're looking at right here. And we've seen transitivity come up in interesting ways. I think we talked about it briefly with division. Those are the three keys for defining an equivalence class. So this relation is much different than example 1. There's infinitely many objects inside this set. And it has a property the last relationship didn't have whatsoever, symmetry itself. Well, again, examples 1, example 2, really just here to get us thinking about what is a relation. For the next examples, we're going to start doing more heavy computations, looking into other interesting kinds of relations. But any questions at the moment? Okay. Well, like we hinted on before, we've seen plenty of relationships already in these notes. And congruence turns out to be a really useful and interesting relationship. We say two integers, a and b, are congruent mod k, writing down this, a congruent mod k to b, if a mod k is equal to b mod k. The moduluses with respect to k are both the same. Congruence turns out it has the property of symmetry. If a is congruent to b, well then b is congruent to a because you can just switch the left and right hand side of these equations. But it has more. It has reflexivity, so we're going to look into that, and transitivity. Kind of harder to see in our example, but we'll see plenty of examples highlighting transitivity. So here's our next new example. A little bit more going on with this one, but this is a pretty, again, very useful relationship, thinking about congruence. To make the problem not too big, I made my set finite of size 10. But this relationship you could define on Z itself, and it partitions the integers in a very useful and interesting kind of way into equivalence classes. So congruence mod 5 is going to be the set ordered pairs AB and X cross X, such that A mod 5 is equal to B mod 5. So in other words, we're just re-looking at this entire definition here, congruence mod K, but we're recasting this whole definition in a brand new light in the terms of a relation itself. A relation is a subset of a cross product like we see here. And so now our major goal is part B. We're going to write down this entire set to see what it is. Part A is kind of the warm-up to get us started. So we have a couple set memberships to consider. The notation is interesting, but again, we're looking into this operation of congruent mod 5 in a new light as a relation. So this is asking, is 2 related to 7? Let's write 2, 7. Briefly consider what happens with that by that relation. Congruence mod 5 just means take 2 mod 5. That gives us 2. Take 7 mod 5. That's 2 as well. That means 2 is congruent to 7 mod 5, but that's all this is all about. Congruence is the set of all possible congruences. So we can say it is an element of congruence mod 5. I'll just say here, since those two operations came out as correct. In other words, the other way to say that is 2 congruent mod 5 to 7. much like how we were saying up here, X related to Y, we just put the congruence mod 5 in the middle. That's a specific relationship R we're using. Let's actually write that down on paper. Let's say here, R, we're just using this entire symbol to fall into place of that relation. So that's 1 down. So if 2 is congruent to 7 mod 5, and we change this, 7, 2, notice the check is exactly the same. It's just a different order. 7 mod 2 is 5 as well. 2 mod 2 is, 7 mod 5 is 2. 2 mod 5 is 2. So there's really no check here. We can just say this is automatically in the set congruence mod 5 because 2 is equivalent to 7 mod 5. Really, these two notations are saying pretty much the same thing, but we don't ever have to duplicate our check. That would feel an awful lot like busy work. But that's the amazing property of congruence mod 5. If 2, 7 is in the set, then 7, 2 is in the set. We can switch the input and output. That's not always a guarantee. But it turns out from congruence, just like on the last example, that actually holds. This is a symmetric relationship. Let's check another one, 5, 4. On visual inspection, you might have an answer already, but let's do the work on this before we say it's inside something or not. I'll say here, since 5 mod 5 is 0, 4 mod 5 is 4. We have different values mod 5. 5 is not congruent to 4 mod 5. And saying that in our new notation, that's just saying it's not an element of the relationship R, where R is congruence mod 5. So these are not related. Then we just go off to the next one. But any questions at all, folks, with our 3 checks so far? Okay, now this one's pretty interesting. This one hasn't come up yet as a topic. Is 9, 9 in the set congruence mod 5? Well, our check is to take 9 mod 5. That's going to be, hang on, wrong number, 4 fingers. That's going to be 4. But then you do the same thing on the next element. 9 mod 5, 4 again. So if you put in the same element, the modulo 5 value is going to be the same as well. That means this is automatically in the set. Let's say here briefly, 9, 9 is in fact in the set congruence mod 5. Since 9 is congruent to itself mod 5. This is a brand new property we have not seen just yet. And we're going to look again in section 8.3 at these properties very, very closely. But this property right here has a name. This is called reflexivity. In our last problem with the unit circle, there is no reflexivity. For example, you can take the element 1. In the last example, I'll put it up kind of high here. R is not reflexive since take an element like 1, ask if it's related to 1. Well, that's not in the set R, being in on the unit circle, since 1 squared plus 1 squared is not equal to 1. It's not on the unit circle whatsoever. So you can't get values like these inside that relationship. But for mod 5, you can put in the same number, any same number in this set, it's related to itself, guaranteed. Well, that's a, again, brand new relationship, mod 5. We'll look into others. But what we want to do now is return to the original definition. Mod 5 is a subset of X cross X, where it's that finite set there. So it's a relation on X is how we'll notate that. I guess we did say that's a relation on X. That means it's a set specifically, and we can now exhaustively list out all the elements of that set. When we think about that, listing this out, we want to know how big could it possibly get. The size of x squared, which is the size of x, Cartesian product, make that a smaller x, with itself, that's just the cardinality of x times the cardinality of x. Well, that's just going to be 10 squared for 100 altogether. So in the very worst case, this relationship could have maximum 100 elements. Probably not that many, but if we come up with 101 elements, there's a big problem somewhere here with our definitions. There is a lot of elements on this one, so it's a good idea to kind of strategize or work carefully. So let's organize by first thinking mod 5 is the big operation here on the set X, 0 through 9. So one thing we can ask ourselves if we're doing this kind of problem, listing out the relationship congruence mod 5, what are all the possible values mod 5 relative to this set? So let's write and organize by saying this, possible values mod 5. All possible values mod 5 are going to be, let's go A mod 5, and one possible value is 0. You can absolutely get a 0 there. But for writing out the set congruence mod 5, we're trying to find out the values A and B. So what I'm really trying to say is, for what A here do we get 0 mod 5? Certainly 0 works. 0 mod 5 is 0. So A would be 0. And 5 works. 5 mod 5 is 0 as well. So A would be 0 and 5. Let me fix my penmanship first. Now let's go to the next value. What about A mod 5 equals 1? Possible values for A when you take mod 5 are 1. 1 mod 5 is 1. And all these are going to come out different. 5 mod 5 is 0, but 6 mod 5 is absolutely a 1. So 6 works. I notice there's already kind of a pattern here. Once we find the base values where it comes out mod 0, being 0 and 5, increment by 1, how do I get a mod 1? What does A have to be? I just go in this column and add 1 to these entries. So following that logic, if we say A mod 5 is 2, possible values for A should be 2. Absolutely, 2 mod 5 is 2, and add 1 here, 7, because 7 mod 5 is absolutely 2 as well. So that's kind of a nice, helpful pattern for our organization here. Then go A mod 5 equals 3. Potential value for A are 3 and 8. Double check mod 5. Those are both equal to 3. A mod 5 equals 4. You know what? These are all the possible values for mod 5, because if we go A mod 5 equals 5, well, we're just talking about this one, A mod 5 can never be 5 is a better statement there. When we do mod 5, we're between 0 and 4 altogether. So this is the end of the list. Only possible values for A are going to be 4 and 9. Since 4 and 9 mod 5 do in fact result in a 4. So now we have all these values, but these are not the elements in congruence mod 5 whatsoever, because recall, they have to look like that, just like in part A where we're checking values. So we know of 3 different values here, and the very last one inside the set. And this is just a structure to help us think about what are all the other values so we can organize and write the answer as efficiently as possible. So here's what the set looks like with the organization column on the left. So congruence mod 5 is equal to a set. Here I wrote it out in words, is the set. If this is not too jarring for you, go for the equals, but make the equals a little bit smaller so it doesn't hurt your eyes to look at those symbols right next to each other. So congruence mod 5 is the set that contains, well, starting here, 0, 0 is an element. 0 is congruent to 0 mod 5. Next, you can put in 0 and 5. If you do the same check like we did in part A, 0 is congruent to 5 mod 5. The modulus of both of these values is the same, 0. We're thinking of that possible value there, 0 as well. But you can change the order of this one. We have symmetry for this modulus operation. So if 0 is congruent to 5, 5 is congruent to 0. And we also have reflexivity. Just like 9 is congruent to itself, 5 is congruent to itself. So we can put 5, 5 as our next element in that set. So really all we've done here is we've taken a set, 0, 5, take the Cartesian product of that set with itself, but write them as ordered pairs in our author's notation. And that's the very first row. Then we go down a line and just do it all over again. So the next set of entries is going to be 1 is congruent to itself. 1 is congruent to 6. 6 is congruent to 1. And 6 is congruent to itself, mod 5. Then that's pretty much the entire name of the game. This is the whole pattern to this. On the next level, you can say 2 congruent to 2, 2 congruent to 7, and so on. Or we could say 2 is related to itself under this relationship, congruence mod 5. 2 is related to 7. 7 is related to 2. And last, 7 is related to itself. Then down the line, 3 is related to itself. 3 is related to 8. Use now symmetry, 8 is related to 3. Use reflexivity again, 8 is related to 8. Final row, this one turned out kind of long, so final one. Here's reflexivity, 4 is related to itself. 4 is related to 9. So with symmetry, 4 is related to 9, then 9 is related to 4. And reflexivity, 9 is related to itself. So that ends the set. And now we can see here that the cardinality of equivalent mod 5 is, let's see, 5 rows, 4 columns. It had 20 elements altogether. So not as bad as it could have been. There's a fifth of the total possible size. It's quite an operation. It got a little bit messy here with the organization, but all we're really investigating is for what possible value, what is the total set for which elements in X are related to this congruence mod 5, through this congruence mod 5 rather. Well, any questions so far, folks, with that pretty big computation here? Okay, well, let's write down on paper just to, again, think about the bigger section, 8.3, the properties we're looking into. Congruence mod 5 is reflexive. Reflexivity is the first column and the last column we see here. Elements are related to themselves. Symmetric. For every single element, every one of them in this entire list, even the trivial ones that go 2, 2, switch the order, it's still 2, 2. It's inside the set. But anything else like 8, 3, switch the order, 3, 8, it's in the set. So that's what we mean by symmetric. Every single element here, we can switch the first element and the second element. And it has something even further, it's transitive. Let's talk a little bit about what transitivity means because we've dropped that word a couple times. Transitivity is harder to see with this set, but what this is really saying is if AB is an element of R and BC is an element of R, then A connects with C, they must be related as well. So that's all transitivity is saying. And we use transitivity all of the time in mathematics. In fact, one relation, a trivial relation, is ordinary equality of numbers. Say elements are related if the numbers are equal. So if that's our relation, we could say let R be the relation on X that XY in R if X is just ordinarily equal to Y, X and Y are the same. That's automatically transitivity because, or transitive. This is transitive because X equals Y and Y equals Z. This is the property we take for granted again all the time. Just means X equals Z. In fact, we usually abbreviate that whole X equals Y and Y equals Z, and we say this in a different way. X equals Y equals Z. Imagine you're doing some algebra here, or maybe you have order of operations, just simplifying things down. You have a train of equalities, but transitivity just lets you take the first thing related to the last thing and come up with that conclusion there. So this relationship does have that property. And we're going to see other interesting relationships as well that has these full set of properties here. These are the magical three. That's what are going to result in something becoming an equivalence class. An equivalence class, its whole purpose is just to extend ordinary equality in a larger sense. So it's an extension of equality as we've been using before. Well, for the rest of the notes, we're just going to practice more with the relations, but this is the big set of ideas so far that we'll come back to quite a bit in the next section. For the next problem, we're just going to look into a couple more properties of relations that will come back here and there. If we have a relation, we can invert them. And we can also do compositions of relations. So those are going to be our last two properties. So first, let's take a look into the inverse of a relationship. Definition says, if R is a relation on A cross B, then R inverse is a relation on B cross A defined by, write R inverse as a set, ordered pairs BA, in B cross A, for which A, B were in the ordinary relationship R. Essentially, all we're doing with this inverse is switching the order. And so if we think back in terms of functions, again, way back in the day, we made that comment as well. We're inverting functions. If AB is on the graph of a function f, but we want to consider its inverse, which would mean the function is 1 to 1 and on 2, that just means BA is on the graph of f inverse. Relations have that same exact property. If AB is in the relationship, then BA, just swap those two values, is in the inverse of the relationship. So it's kind of satisfying that all these properties kind of align just nicely and neatly in that kind of way. And here's our new relationship to consider. AB is going to be an element of R if A divides B. So this relationship R is defined on the set X cross Y. Here's our set X, here's our set Y. And if you preferred, again, our author primarily uses this as his dominant notation in all of the reading. So I'm keeping that similar as in our notes as well, so the reading doesn't seem so different. But you could just reformat this in a new notation by saying A divides B is essentially the entire relationship R. So this is using A related R notation. But if the relationship is divides, we can just put in our vertical bar notation from all the way back in section 7.2 to say it in that way. So either way you decide to say it, you're really talking about the relation. So again, just for emphasis, we're going back now to 7.2 and just redoing this whole definition, the meaning for what it means for K to divide N. It means n divided by k is an integer, which would mean we can write out this fraction equal to another integer, which would mean that you have this property here as a multiple, or that just n mod k is 0. So that's all this relationship R is all about. So you could relate this to this down below if you prefer, or just keep it in this format. So notice, even though we're changing to a division relationship, it's still a modulus problem really at its heart. First thing we're going to do is just write down the set R, and then we'll write down the inverse of that set. So R, as a set, is a collection of elements, A cross B, like we see right here, but the A values are going to come from X, the B values are going to come from Y, and the relationship is values from here divide the values in the opposite set Y. So one good way to kind of build this one out a little bit faster than the last example is kind of make a correspondence. Take 2, distribute it through, and just check if divisibility works. So is 2 related to 3? No, 2 does not divide 3. So then we just move on to the next. 4? Yeah, that works. 2 is related to 4 because we can write down a true statement. 2 divides 4. Then just keep on going down the line. It does not divide 5, but it does divide 6. So the next element is 2 is related to 6. Does not divide 7, so we go back to the set X and just repair these elements. Now, how about 3? 3 is related to itself because 3 divides 3, so we can say 3 comma 3 works in this relationship. Then it divides 6, so 3 6 is inside this relationship. Does not divide 7, so we move on to the last entry, 4. Going through this list, it only divides one element, itself, 4. So the last entry in this relationship R is 4 related to 4. So as a set of ordered pairs, whether you use our author's angled brackets or ordinary parentheses, I'm going to leave that up to you for your notation. That's the relationship R, just 5 total values. Again, different kind of relationship, similar to modulus at its heart. But any questions or comments with the first part? Okay, really the whole heart of this problem is inverting. The inverse is going to switch the sets. It's a relationship on Y cross X this time. And all it's going to do is take all the elements inside this set and reverse the order. Notice sometimes when you do this, nothing happens. For example, in this big set here, if you took a look into, put in yet another side comment, if you look into equivalent mod 5 inverse, what's that going to do? It's going to go to every single entry, swap the values. But if you swap all these values, nothing happens, but that's because it's reflexive. The swap of every single value is already here, so swapping the values gives you the same set. So congruence mod 5 inverse is congruence mod 5. Nothing new happens in that set. So sometimes the inverse is interesting, other times nothing whatsoever is going to happen. You know, it's similar with ordinary functions. The function y equals x, it's its own inverse, so it's not a total surprise. Here, something new does happen, though. If we write out our inverse for this situation, swapping these ordered pairs, we're going to get 4, 2. 4 is not related to 2 under the ordinary relationship because 4 does not divide 2. 4 is related to 2 only in the inverse relationship. So in a weird way, this is the inverse of division as a relationship. Then keep on going. Next one is 6, 2. 3, 3, change stays exactly the same. 6, 3, And 4, stays exactly the same as well as 3, 3. So there's our inverse. It has the same exact size, but different structure. The follow-up question is, what property do the elements in the set have? And there's a lot of things that you could say here. One thing that kind of pops out on me is when you look at that 4, 2, 6, 2, 3, 3, 6, 3, 4, 4, well, we were dealing with modulus really when we think about division, but there's still a pretty good modulus relationship here as well. You could say AB is an R inverse. A is the inverse relationship to B, said a different way, if and only if we take, let's make sure we get the order right. I want to say A mod B is 0. Let's check that out. If that's the A, that's the B. 4 mod 2 is 0. 6 mod 2 is 0. 3 mod 3, 0. And similarly, all down the line, 6 mod 3 is 0. 4 mod 4 is 0. So that's all that's going on with this. In terms of modulus, again, we could have wrote this as a modulus expression as well. Essentially, all that's happened is if you write the inverse as this kind of modulus and R as another kind of modulus, you're just switching the A and the B on one side to the other. So R inverse is not about divisibility. You could cast it in terms of multiples, or that the elements modded in this order came out as 0. Well, we did it, folks. We've inverted a relationship. Again, these are not too tricky. The follow-up question is sometimes kind of a head scratcher. So if you get stuck on any kind of follow-up question like that, say on the homework, don't hesitate to ask either in class, email, or office hours. I'll be happy to help. The R inverse really is just mechanically switching the order of the relationship. Next thing we'll take a look into that is a little bit trickier, in my opinion, is composition. Function composition is one of those things that you have to look at really carefully the first time you're doing, say, a pre-calculus college algebra type of course. And same in this case, if we're doing a composition of relationships, we need to track the definition really carefully. Another thing that's weird about composition is in algebra and in this textbook, compositions go in the opposite order. So if f of x is root x itself and g of x is x plus 3, then we can say g of f at x means you take g, plug in the f of x, which is root x. But notice we're doing f first when we do this. Then this becomes root x plus 3. So this is g at f at x. Sorry, I kind of squoze that in there. We move from the right and go to the left, and we do these kind of compositions. Same idea for the definition for relations. So let's track this definition really carefully. I feel like this is the trickier problem in the whole set of notes. If R is a relation on A cross B, and S is a relation on B cross C, notice that there's a link in. Those sets have to be the same to match up, link together, in order for this composition to make sense. The composition of R and S is going to be a relation on A cross C. So we're going from the outer sets, we're jumping from the set A through the intermediary set B, all the way to the set C when we write S composed of R, much like a G of composed of F. But we go right to left when we read this out. So the property here is S composed of R is going to be a collection of elements AC will be in the composition S of R if and only if there exists a B in the intermediate set B such that AB is in the set R and BC is in the set S. So even if you color code one thing, I would say it should be, I guess it's two things. If you were to only color code two things to kind of unwind this definition, see how it tracks through, it's about that element B. the common domain be, you could say here, or codomain on this one and domain on this one, thinking in terms of functions. If you have a common element B in the second coordinate, common element B in the first coordinate for the sets or relations R and S, then that is your element in the composition, S of R. So let's give this a try. I have a relationship R, just these 5 order pairs, same with the relationship on S, just a random relationship this time. No interesting structure like divisibility, congruence. They're defined on the sets 1 through 6. And we want to do the composition S of R, listing out all of its elements. So S composed of R, that's a brand new relationship, which means it's a set. It's a collection of ordered pairs. And our job is to find all possible ordered pairs inside this set. But let's think in terms of what this is saying. We start with AB being in the element R, because once again, we do the relationship R first. We're moving right to left. So I have a 2, 2 in this relationship R here. I'm going to temporarily highlight this as a 2. If I can find a 2 something in the relationship S, we can link them together and it's inside the composition. But notice that doesn't happen. None of the elements in this relationship S starts with a 2. So that means we have to skip to the next element here and ask, what about 1? 1 is going to be the thing highlighted blue here in the relationship R, but we move to the relationship S and see if it ever starts with an element 1. It absolutely does. It links up with these elements. So that means this element 5 and this element 4 inside those ordered pairs are the new element. Oh, I was highlighting the wrong thing, sorry. It's the new element that's inside the composition, S of R. So we take the 5 we see here. The 1, excuse me, not the 1, rather that was the intermediary value. The 4 that we see clear out here following the color coding, and that's one element inside of the composition. Again, it's tricky because we're jumping through different sets, leaking together the first coordinate and the second coordinate into the composition. Does that make sense to folks on that first element there? Okay, let's keep on going then. Now, when we see 2 come up, we already checked. Nothing in the element, or excuse me, in the set S has a first coordinate with 2. So we just skip on to the next one. 5 comes up here. And here as well. So if we have a 5 here, or excuse me, I think I'm mixing up my notation on this. Let me start over. I was getting mixed up with this 2 here. When we look at this element, let me just review my color coding a little bit more strictly. We're thinking of the second coordinate, not the first coordinate's 2. So misspoke on that. Let me backtrack. And the definition is pretty critical on this one, following it really closely. On the third element in the relationship R, we have a second coordinate of 3, and we hope it's an intermediary value. That will only work if there's a second coordinate, or excuse me, a first coordinate of 3 that occurs. It does occur here, so that's this part of the definition. That means we can link up 2 with 4. So that's the 2, 4 that's inside the composition. So 3 and 3 link up in that kind of way. That means 2 is related to 4 in the composition relationship. So let's go 2 is now related to 4. Again, pretty tricky on these things. Let's follow this a little bit more strictly on the next values. I want to look into the second coordinate on the relationship R on every element. That second coordinate is 2. but there's no first coordinate in the relationship S that starts with a 2 whatsoever, so we move over to the next. On the final element in the relationship R, again, let's do this really strictly, very literally. Look at the second coordinate. It's a 1, so that's matching up that part of the definition. If that 1 here is a first coordinate in the relationship S, we have a new entry. So we have a 1 linking up with a 4. Hang on, where did I highlight that? That was 5 through 1. Yeah, so this 1 does in fact link up with a 4. So when we go from a 2 to a 1, the 1 being an intermediary value, and 1 goes to a 4, that means we can link up those two values here. 2 is now related to 4 in that kind of way. So we can make this jump from here to here. And 2 is related to 4. Let me double check that really carefully though. Any questions or comments so far? Okay, well, we've got it, folks. That's the composition S of R. Again, a pretty tricky process. I think this is one that you want to really follow the definition as carefully, as closely as possible when going through it. And a little bit of color coding is not a bad idea just to get the hand on this. Next question says, what if we change the order of the composition? That's a natural thing to do in mathematics, right? If you're changing the order of composition, instead of saying g of f at x, you'd be doing f of g at x. That means we go in this order, f at g of x, but we're moving really right to the left. We do a substitution for g first. G is x plus 3. So this is f at x plus 3. Then that's the input to the f function. So x plus 3 goes here, and we're really looking into the square root of x plus 3. And as these two fast examples kind of highlight is the order of the compositions do not necessarily give us the same values. If the functions are related by one being the inverse of the other, they will give the same values. They're going to come out as the same exact set. So here, if we change the order of the composition, R of S, and do this whole thing all over again, here we need to be really careful because we're starting with the set S and going to the set R. So let's think in terms of how we did part A first. We're looking for a value on every single one of these pairs. Look into the second coordinate, and that second coordinate must become a first coordinate for the set R, the one that comes second, reading right to left. 4 never emerges as a first coordinate, so we just move down the line. On the second element, look into the second coordinate 3. There is no first coordinate 3 whatsoever, so this element doesn't connect with anything when we compose the relations. And carefully checking everything down the line, certainly no first coordinate that has a 6 at all on this one. So the third element doesn't link up. Here, we've kind of done this check already, right? The second coordinate on both 3, 4 and 1, 4 is a 4, not our first coordinate anywhere here. So that check is designed to fail as soon as the second coordinate here didn't work out. So we move on to this one. This one is our second coordinate, and 3 never shows up whatsoever as a first coordinate, much like when we did the check 5, 3. That means no elements link up with each other whatsoever. That's definitely weird, but it can absolutely happen. In this case, our set R of S is Nothing. It's just the empty set whatsoever. So the order of composition is very critical. If we switch the order of the composition here, we got nothing. It's just a total empty set. Let's emphasize that, the empty set. Well, any last questions or thoughts whatsoever, folks, getting through this one? Yeah, good call. You know, something was bothering about me on this one. I was looking at this and my eyes were seeing three elements, no matter how hard I looked at this. I was expecting two, and you're right. This one, the best way to write this set, because sets only include the unique elements, should just be 5, 4 and 2, 4. Somehow when I wrote this down, my brain just did not see that duplicate. Thanks for mentioning it. So this simplifies to that set. This is considered the best answer for sure. We should always eliminate the duplicates whenever they occur in a set. So yeah, we only had to write that 2, 4 just once. Thanks for spotting that. Other questions or comments at the moment? Okay, well, we just have one last topic to take a look into on these notes, but really it's just kind of here for the sake of, or formality. It's a reminder of what we said at the very start of these notes, that when we talk about relations, it's really nothing new whatsoever. If we went to our original definition of a function, we mentioned we can write our function f as a subset of a cross product. In that sense, here's the new definition. Let a and b be sets of function f, and any function like the square root of x, x plus 3, like the ones we wrote above, written as a function from a to b, is a relation in fact on a cross b. So you could do a completely huge change of view on any function you've ever encountered, no matter what the subject, algebra, calculus, linear algebra, so on. Any function you found, it's just a set, a subset of a cross product, A cross B, where A is your domain and B is your codomain. The only thing that makes it different from a ordinary relation like the ones we're studying is, if we call it a function, it just means the function has a relationship that if A is an A, there's only one unique element B in the set B, such that AB is related through the relationship F as a function. Or you could say AB is in the set F. So now we can view sets like, say, square root X as being literal sets, any function whatsoever. Again, it's kind of a strange point of view, but that's how our topics loop back on each other. And that's what relationships are really all about. It's just extending this definition. What happens when you peel off that part right there? Then just becomes a bigger concept. So here's our next problem to take a look at. This is a bona fide function from Z6 to Z6, where Z6, the set of integers congruent to 6 are 0, 1, 2, 3, 4, and 5. We'll write down f by listing out all its elements. And here's the ordinary function notation for f, so it's pretty fast to write down f. But if we're saying listing all of its elements, we mean that listed as a relation now. So we're changing our entire point of view of functions. The way to work this one is go to set, just do all the function evaluations. F of 0, here's the definition, would just become 4 mod 6, which is 2. But then that would mean in our answer, F is the set that goes, take this value, the input, 0. It's related as 2x plus 4 mod 6 through the function f to the output of 2. So again, that's pretty much all we're doing here, writing down the function now as a set. Then it's kind of rinse and repeat. This is kind of the relaxing problem for the day after the composition one. F at 1 means we're taking 6 mod 6, but 6 mod 6 is 0. So the next element of the set f, go to the input 1, throw in the output 0, and we'll have 4 more values. Take f at 2. That's going to be 4 plus 4, so 8 mod 6. 8 mod 6 is 2, so we have the element 2 comma 2. Next is element 3, f at 3. Means we have 6 plus 4, so we're just doing a 10 mod 6. 10 mod 6 comes out as a 4. Becomes pretty methodical. Now link up that and that as the coordinates, 3, 4. And just 2 more to go. Take the 4, compute f at 4. Go to the definition, that's going to be 8 plus 4, so that's a 12 mod 6. 12 mod 6 is 0, so that means 4 is related to 0 through this relationship. And final value, 5. Take f at 5. That's going to be 10 plus 4, so we're looking into 14 mod 6. Output's a 2, so that means 5 is related to 2. So is this in fact a function? Well, if we look into every first coordinate day, they are 0, 1, 2, 3, 4, 5. They only come up exactly once. So that means every first coordinate, A, has exactly one element, B. 0, 2 doesn't come up again as 0, 3, for example. The first coordinates only show up exactly once. So this is a bona fide function. Now, it is not one-to-one. It is not on 2. Plenty of duplicated values. So if we're thinking in terms of section 2.5, we would say f inverse does not exist. It loses those 2 properties, one-to-oneness, on 2-ness. But we have a whole new perspective in section 8.2. As a relation, f inverse absolutely does exist. It's just no longer a function necessarily. So if we were to write down f inverse, here's all we're doing. F inverse is the new set. Just swap the order of all these coordinates. 2, 0, 0, 1. 2, 2 does nothing functionally, same value. But most of them are different, like 4, 3, 0, 4. Last is 2, 5. So that's all f inverse is. It's a whole new kind of relationship. These sets are totally different now. And we wonder, is it a function? Well, if you take a first coordinate 2, a 0 comes up, but then 2 comes up again, and it is related to 2. It doesn't have one and only one element B inside this relationship, like a function would have. So this is not a function at all. We can say here, f inverse is not a function since 2, 0 and 2, 2 are in f inverse. So if we're thinking in terms of a function, we would be saying 2 maps to 0, but 2 also maps to 2. We broke our function. We violated, say, a so-called vertical line test, in other words. So it doesn't matter which definition we're looking into, the formal definition here or the brand new definition as a relation, same idea. The inverse is not a function whatsoever. But it's absolutely a relationship. It's just a collection of ordered pairs in Z6 cross Z6. So we can say, however, f inverse is a relationship borrowing our author's shorthand notation. If the set A and B are the same, we would just say a relationship on Z6. So again, it's kind of a fun sort of follow-up topic, looping back what we know about functions But now forcing it into the definition of a relationship is natural. Just be careful with this part. Our algebraic training is going to tell us F inverse doesn't exist, but it does now with our new definition, our new landscape of where relations really are. It's just not a function in its own right any longer. Oh dear, sorry for running up right to the minute and past it. Any last questions or thoughts at all, folks, before we call it a day? Okay, well, this is our tour of what relations are. Our major goal when we come back on Tuesday of next class is visit these topics: reflexivity, types of symmetry, and transitivity. So really, we're going to be doing the same, just looking into more relationships and focusing on those properties a little bit harder. But have a great weekend, folks. Thanks for your hard work on getting through the third exam. I'll be grading them on Friday, hopefully to get it completed by Friday, possibly later on in the weekend. But we'll be back to this on Tuesday's class.